Okay, of course, in 2 weeks we have to finish this task, and then we can create flow simulation. It's not so, yes, finish. Same story, yes, I have other part, right mouse button, insert method sweep, same procedure, inlet, outlet here, outlet other side, 20 elements, everything same, yes. And one thing more, before we start in simulation, yes, we need to say to program this ordner, yes, program doesn't know ordner, and we need to understand how it works. So, I make generate mesh here, okay, it looks bad, I say again, maybe size in 2.5, for example, not so big, maybe bigger, yes, it's okay. Then I can say here again, insert method sweep. Okay, one side, other side, without number of divisions, yes, it's automatical have to be. So, program connected these two parts, automatical, generate mesh, you see, okay, it looks okay, yes, maybe we need to do it finer, sizing, 2.5 for example. Okay, we will see it's optical, how it looks. Okay, it looks okay. Then we need to create, okay, it was 2 in lectures, 2 and 2.5, yes, okay. Okay, I can do like in lectures better, 2 millimeter and 2.5. So then I can delete this meshing, create meshing, then create next meshing. So my bolt is not sweepable. Then I can say insert method multizone. Multizone means program try to do it itself, so to slice geometry. Look, for example, multizone element size, like in lectures 2, insert size in 2, and then we will see what's happened. We will see exactly that the program sliced this geometry. We will see exactly it. Look, yes, if you show how your geometry looks like, you will see the program slide. Yes, like I told you, yes, if you slide here, then you can sweep this body. Yes, you see here exactly radius, yes. So the program slided this geometry automatically and then connected it. Yes. So, and last part is like in lectures is okay, 2 millimeter also. 2 millimeter, insert sizing, 2 millimeter, and we will see also it has a mesh. So, and now I did my meshing, yes? I have only hexa meshing. How many elements? I have knots, elements is not important. Knots is decided system of linear equations, yes? Knots multiplied with 3, so many system equations I have. So, 3x, y, z limits, yes? Okay, I have about 60,000 knots, it's very good. And net looks very good. What we have to know by ANSYS, yes? Now we have not one part, we have 3 parts, yes? And we have to say to program which direction, what is first, what is second, what is third, yes? For example, if I make, if I had 20 parts, yes, then in 2 days I have forgot what is first, what is second, yes? So it is better to say to program from the beginning what is the first, what is second. So how I can do it? Look, if I push this main mesh button, okay, I have this mesh, yes? I can delete here mesh, clear generated data, it means I delete all mesh, full mesh. So if I push this button now, say generate mesh, what's happened? I don't know. Program don't know ordner. Program makes something, it looks good now, yes? But normally it comes mistake, error, it's not possible to connect it, for example, yes? So, and here it was no problem, but normally it has to be problem. Okay, it looks different as I want, yes, it has 50,000 nodes, it's different, yes, it means program tried, made maybe maybe first this part did, yes, and then this part, look, and then error, yes. If program decided to make meshing for this part first, then we have error, mistake. We cannot connect these two parts, yes. And we need to say to program this ordner. How we can do it? This is the last point for the meshing for our lectures. We need to say to program which ordner we have for the meshing, and you will see it in lectures. How I can say define mesh order. It's easy. We have one button here, worksheet. If you push this button, then you will see this field. We can delete all our meshing first, clear generated data. We delete our meshing first, and then we can push start recording. Start recording means I can save my order. So my order, what is first, what is second. So I say start recording, then program save this information. I go back from worksheet and then I say step by step. So first this meshing, generate. So then program saved it. This was first meshing. Then I say this meshing is second, and program saved it. Then this meshing is next one. Okay, this meshing is next one. This meshing is next one, and then bold, for example, and second part of bold. So generate mesh. So. And then I can go back to the worksheet and I see program saved, yes, my steps for the meshing. So what it means if I push now this main button of mesh, yes, if I delete this meshing, and if I push this main button, then it comes my ordner, what I defined, yes. So I don't need to push now separate parts, yes. If I saved it one time, then I can push here mesh, generate mesh, and you will see program makes what I first told, yes. What is first, what's second, what's three, what's four now. So it was all about meshing, yes. Okay, and now we can calculate this meshing. Okay, we can also we can show statistic of meshing by I think quality. We can say mesh metric element quality, and then in the element quality we will see which kind of meshing we have. You see we have always hex 20 nodes, and sometimes pyramidal we needed to connect it. So it's perfect mesh, no tetrahedrons, yes, super good. So okay, and it's only with some small things, yes. So okay, we created good meshing. Did you do meshing? Everybody did meshing. Okay, we are waiting 5 minutes. Please do what you have. You do meshing. Good.
Yeah.
Good. Okay. And we will see what is the difference, how we can use this difference,
This is for examination.
and how we can say is it safe or not. So, okay, important knowledge it was for today to understand that program control is not the best solution. So, we have many points in ANSYS, like program control, it means program decided, but we will see if you understand a little bit how it works, we can do it better. Yes? So always program decides something wrong, not what we want. Keep hiding. Es muss so sein, so wie war es, der Mensch ist einfach so wie war es. gleiche Quetschen, gleiche Rufen, das muss eine Geometrie sein. Das Programm soll lieber scannen oder nicht. Zum Beispiel Kekse, aber auch nicht an der Zeit nicht mehr zu machen, weil es ist die Frage, wie kann man diese Tetramesh soll gleich 3x soll gleich nicht sein, mit 60 Grad egal was. Ja, und das war der große Schritt, wie man hat Methode gefunden, wie kann man jetzt so viel messen, dass es so mit 60 Grad Winkel wird. Und dann hat ein Mann, keine Ahnung, 20 oder sowas, ja, und jetzt jede Software benutzt das. Aber nur für Tetramesh, das funktioniert nur Mesh. Aber ist doch, das Programm ist nicht in der Lage. Okay, warum? Wenn wir nur Volt schaffen, in der Rechnung, dann ist in der Lage. Dann machen wir es schon selbst. Aber, ja. Das ist nicht, warum Sie nicht in der Lage, was anderes zu machen als nur Meter? Bis jetzt kann ich nur Meter einstellen. Und das mag ich, weil ich bin nicht sicher, ob es ist. Okay, how we can do, we have all knowledge to do the simulation. All knowledge in the world, we have this task. First, we have two steps. First, we have press stress of the ball, yes, and then we have fluid pressure. It comes, it goes down, 0,5, 0,5, 0,5, yes. The question is, do we have problem after 1 million, for example? This pressure loads or not? Yes? So, okay, how we can answer this question? First, what we have to know, and maybe in the next lecture we will speak about solution of linear equation. We have to define boundary conditions first. So, okay, we know how we can do nonlinear simulation now. Yes, we have to define nonlinear material properties. Yes, with this Excel file. We will find an internet table. Yes, with points, and we will use Excel file. Again, I repeat, this material properties. We will use Excel file.
The same one that we use?
Yes, same one. Here we will write what we will find on internet. Then here we have this bilinear canlinear, yes, line. Ideal, it will be better recalculated in true stress to strain. Yes, if our deformation big, then ANSYS calculated always with true stress, true strain. Yes, it's always exactly solution. But you see, if deformation not so big, like in our task, yes, if you have big deformation, then it doesn't work 1 million times. Yes, we don't need to calculate it. So, and normally it's enough to do like this one. Yes. But if you correct this, of course, true stress, true strain. So, but you will see it's not so big difference between if we don't have big deformations. So, okay, for your practical work, it's enough if you do only this bilinear line. Yes. For simulation, then we have to say material null effects. Yes, we have to say ledge deflection on, and we have to say RSX no. So, and then we can be sure that it's correct. Okay. First step. Okay. What we have to do? We have to do all these things. Yes. Okay. Mesh is works. Yes. Okay. We have mesh. Then we can close our meshing first, and then we can go back to the material properties. Okay. Then we can make duplicate, maybe our steel duplicate, and we will give the new name for the steel 1.4435. We found it before in lectures, material properties 4435. In your practical work you have your own variant 1.4435, and we have to define material properties now. So how we can do it? Here plasticity. Yes, bilinear, kinematic, for example, not important. Isotropical, kinematic we are doing like in lectures. With drag and drop, we can add these properties in our material properties, yes. Then we have to change our Pascal to megapascal. And then we will write these calculated properties, yes. So we calculated this 2 lectures before, I think, yes. So it was here about material properties, yes. And we calculated this here, this material properties, yes. These 2 points we need in ANSYS for the simulation. So, okay, tangent modulus and Dengrenz, yes, tensile stress. So, okay, tangent modulus and yield strength. Okay, we will write here like in lectures. Like in lectures, we need to write here these properties. Okay, where is it? Okay, we need to write these properties. Yes, here you can find the slide. 318.8 is our yield strength. And then we have tangent modulus 618.5. So then we defined our material properties. So, okay. Then we can go back, close engineering dates, and we can go back to the model, yeah. And then we need to do these all steps, RS6 no, and large deflection on, nonlinear effects yes, and material properties, this new material, 1.4435. So, okay, this is what we need to define first, before we start with simulation. So we have to go to the geometry, and for every component we have to change steel to 1.4435. So then we need to change our material, non-linear effects yes, standard now. It was before not standard, yes. Okay, yes, and here 1.4435, 1.4435.
Everything.
Everything, yes. Everything is, we will say material. Okay, this still is linear properties has now, yes. And we want to do non-linear simulation, we need of course non-linear material properties. So we defined it. Okay, and then we can go, what we have to do, in analysis stating we will say ledge deflection on, very important, yes. Ledge deflection on means geometry will be changed during calculation. So, yes, our geometry is also always changed. And then we will say RS6 no. How we can do it? With command. Right mouse button, static structural, insert command, and we will say RS6 no. It means no interpolation, yes? Then we see correct results.
Where did we take this?
Or
From where did we take
or
the
on.
comment?
No, I write it every day. No, yes, RS6 no. Okay, and then important.
We have a static.
No, it's not now important. We don't see it now. Okay, later. Okay, we defined it, and now we have to repeat lectures. Yes, our all boundary conditions. So step by step. First, symmetry boundaries. Of course, we have to say to program we have symmetry. Yes, how we can do it? Okay, first we don't see symmetry here. It's also something new. Yes, normally we see here symmetry. Program, we need to add this point. Yes, if you push right mouse button by model, insert symmetry. Yes, then you can add symmetry. Program have to know that we have symmetry. Insert symmetry region, and then we can say here where we have symmetry region, we have this gap field, and we can choose this field and say this all faces is symmetry faces. So all faces here, this side is symmetry faces. Then we say, okay, also here, we say apply, and important, yes, it's a mistake that we have always this mistake, which direction is normal? Yes, normal, okay, we need to say to program symmetry and which direction is normal to symmetry. So, oh, please write it to me. Thank you. So, which direction is symmetry? Yes, it's very important. For example, in my geometry, yes, I see here is symmetry and direction is epsilon, yes? So normal, 90 degrees is epsilon. So then I have to change it here x to epsilon. And this is the first symmetry, but we have two symmetries, yes? We have other side is also symmetry side. Okay, I can choose again all faces. Here right mouse button, insert symmetry region. And which direction is x? So, okay, symmetry we defined. So the next step is symmetry. The next step is contact. Yes, contact. We need, of course, to define all contacts between parts. Look, automatical programs showed us which contacts program sync. We have, I don't know, 6, 7 contacts, yes. But do you see it's always, yes, by contacts sync program, it's all parts are separate. And it's not good, it's better to delete all contacts, automatical, and to create every contact for every part manual. So, okay, we have only 3 contacts normally, yes? We have contact between bolt and flange, then we have other side contact, 4 contacts, yes, then we have here contact and here contact, yes? So, we have 4 contacts, and then we need to define this all, yes? Okay, we can start from here, for example, yes, we go into the contacts, right mouse button, no, here, contacts, insert manual contact region. So, manual contact region, we will say what is the contact side, what is the target side. We can say, for example, okay, look, I want to show you some thing to do the contacts. Very important thing. It's help to define contacts. Look here, you see explode factor. Try to do it. It's like explosion. You will see that. Try to do it. So if you do it, you see all parts go separate, yes, and then we can choose all faces. So for example, now I cannot choose face here between, yes, I have to hide something, yes, one part. And if I do this explosion, I can all parts, yes, all bodies, it's one body, go out, and then you can choose everything, yes. So, okay, it's easy to choose with this function. Okay, for example, first contact between this face and this face, yes?
Wait, what? What contact?
Okay, I have, for example, first contact bolt and tube, yes? So, how I can do it? Okay, I can say explosion, then I can say insert manual contact region, and then I say this face contact and this face apply. So then I can go back with my explosion. So, and I see here right contact side, target side. Yes, it's correct. And then I can say this contact is not bonded, frictional. Normally we have Revin contact with friction. Yes, frictional coefficient is 0.1. We say so. Frictional contact between parts. with 0.1 coefficient, and okay, this first contact. Second contact is between two tubes, yes? I say again, insert manual contact region, and between two tubes I have contact. It means these two faces and other two faces, yes? So, same contact type is frictional 0.1. Steel 0.1. So, then we define the next contact. Then we have contact number 3. Again with the bolt, manual contact. Again, I have contact between this part and this part. Frictional again, 0.1 coefficient. And the last contact between bolt and mother part of bolt, yes. And this is bonded normally, yes. So, okay, we don't have real geometry, and we can say contact between these parts is bonded contact, manual contact region, and so between this part and this part, this face, these two faces is bonded contact. So, and we have 4 contacts, and we defined these contacts. Everything is good. So, okay, you can find every step in lectures, yes? So, 4 contacts, frictional, bonded. So, then we need to define, of course, our boundary conditions for the loads. Okay, we have 2 steps. First, we have 2 steps of simulation. It's always 2 steps. We have pre-stress is always separate, yes? It's normally, our question is this fatigue, yes? Fatigue, I have 1 million times this pressure loads. 0 max, yes? And my pre-stress is always same, yes? Then I need to separate this pre-stress. Always? Okay, and it's easy to control. Is it always correct? Then we have 2 steps by simulation, and we need to say it in program. We have 2 steps by the simulation. Okay, analysis setting we are going, and then here you will see number of steps, yes? Number of steps, we will say 2. We have 2 steps. And then if we do it, then we can define boundary conditions. So, like in lectures, look at, yes, here. Okay, first is preload. How I can define preload? It's easy. We have this function in ANSYS automatical. So, function is, if you go to the boundary conditions, we have force, pressure, we did it before. Yes, we have everything here, force, pressure. You will see here ball pretension, yes? You will see bolt and you see it's bolt. So, and we can choose this bolt pretension, and program asked us geometry. We can choose face, yes, where we want to do this bolt pretension, this face of the ball. So, face, this face,
No.
and then we say apply
Which face?
this face
Ah.
of the ball. Or I think it's not a problem if you choose full body. You can try to choose it. The full body, then its coordinate system is wrong. Okay. No, it's better to choose face. But full body is also works, but coordinate system you need to define. So normally like in lectures. So okay, we see that in this position we will simulate this body. So and it's okay. If you do it later simulation, you will understand what's the problem if we choose full body. So, okay, phase, and then it have to work. Okay, and then we need to define, of course, boundary conditions. Here we have this table. Yes, table has 2 steps. And we need to say, okay, first step we have preload. Yes, 16 kilonewton. For half model is 8 kilonewton. Preload, 8,000 newton. Yes, first step 0 second to 1 second is preload. And second step we want to say here not load but lock. So lock. Lock means I do 8 kilonewton and then it stays 8 kilonewton. Yes? So it means if my temperature goes high, then it will be of course less. Yes? So automatic. So if I say here 8,000, it means if my temperature goes high, then program try to compensate with 8,000. Yes? So we say 8,000, 8 kilonewton and log. So we have 8 kilonewton and like in reality, yes? And we do nothing more. Okay. And then we have to define second step for our simulation. Second step is pressure. Okay, of course we need to fix something, yes? So, okay, if I do now pressure, then after simulation start, my parts moves in the far away, yes? So I need to fix something, yes? This is a tube connection, and normally I can say without problem this phase not fixed, but this place is in, for example, in my axial direction fixed, yes? So this is tube. It means it's going to go outside, yes? But I have always here one tube, yes? If tube long, I have always this tube in this place, yes? I can say something I have to fix, yes? So I can say this phase, remote displacement, we use it before, yes? Insert remote displacement, and by remote displacement we can say exactly, for example, only axial direction is fixed. Other directions are free. Okay, rotation also fixed. Okay, in my simulation Z is fixed and all rotations are fixed. So, but X epsilon is low, yes? It means it can be, diameter can be bigger. So, okay, we did it. Okay, in lectures it's only fixed, yes? We can also rotation, it's not important to fix. Okay, we have symmetry, it means it's not possible to rotate, yes? Symmetry means also like fixed. Okay, so we did it. And the next step, we have to define pressure, of course, yes? Pressure is the last step for the simulation. We will choose all phases. Yeah, in the middle of tube, right mouse button, insert pressure.
The one between them?
Between where?
On the top.
Here.
Top.
No, it's like tube. Yes, we have only inside.
Yeah, but the inside between like the door.
Where?
This.
Here, top.
No. Like.
Yeah.
This is important place. Yes, this place just distract our part. Yes, we have here pressure and a lot of force, and this force distract our parts, our connection. So, and we say here, look, first step we don't have pressure, 0, and second step 5 megapascal. So pressure. Okay. And in principle, we defined everything, yes? So, what we want to control? We want to control equivalent stress always, yes? Our result is always equivalent stress. We can say from the beginning we want to show equivalent stress at the end. And now we can start our simulation. Yes, we define everything. We define geometry, material properties, symmetry, contacts for meshing good. Then we have set ledge deflection on and LS6 no, gold pretension, remote displacement, pressure. Everything is okay. We can start our simulation. And we can control not solar output but force convergence. We can always, what we want to control is force convergence. So what's happened? We will see now how simulation works. And this simulation is maybe 10 minutes or more. Okay. Please try to go to this point, yes, to start simulation. Next, in 2 weeks, we will finish it with some things, but you need to start. And somebody who wants to show me that he started, then he will get 1 point to the plus. Okay. I see.
Thinking to stay here today and work on
Today. Tomorrow we Friday.
Friday. Tomorrow we have to. No, we don't have that.
Why? Tomorrow we don't have that?
Tomorrow we are
Okay,
going to
what we see now, this convergence,
second
yes?
report.
It's like soccer now, yes?
See.
We are, our hope that red line goes under blue lines. If it happens, then we found the solution. So, look what's happened. Program tried to calculate 0.2 seconds, yes? 1 second is 8 kilonewton. It means program tried to calculate 8.6 kilonewton. So, this is error. That is okay. This is my error actual. It means if my error less than maximum error allowed, then I found solution for 0.2 seconds. Yes? The program, every step, program tried to program calculated system of linear equations. Calculated and then checked, yes, for example, left or right side, and it's not correct, yes? Then it's error. And error is too much. Then program calculate again, and it's happened, yes, until it's enough. For example, if this line go row up, then we will see red line, and program try to calculate 0.1 second, for example, less force. So, but now look, 8 iteration, and we found solution. What's happened? It's very interesting to watch in all days. So, these lines. What's happened? Look, program found solution 0.2, and then program tried to find the solution 0.4. Do you see? And here we see green line, and program tried to find the next solution. And it will be easy, yes? If you have solution for 2 kilonewton, it's logical, easy to find solution for 3 kilonewton, yes? Look, 2 calculations and we found solution.
Green is the solution. Green line is the solution.
So, and then we have to wait.
Second. Some iteration is going on.
Bro, I am not able to do
Yes,
this. In this step,
Yeah, it can be different.
he added
As
the
a
order
machine,
for the machine. In
can be,
worksheet.
as a program control
I'm not able
parameter.
to
2, 3.
I'm not able to add
Look, 0.7.
in the worksheet. It only shows right button, then generate mesh on selected bodies. When I do that, it's not good. Right button.
Okay, and now maybe the main thing that I want that you know. Okay, it works, yes, we found 1 second, look, and then we'll try to go to the next step. Second step, very important thing then, that you have to know how we can do our simulation. It's the basis, yes? Basis is solution of system of linear equations. This is the main problem by simulation, yes? We have n in the power of 3 multiplications, yes, for the simulation. So, the people try to do something to do it quickly, yes? And every software has two types of methods. Type of direct method, iterative method. It's interesting to understand, yes, this difference.